Welcome to the last day of NDC and to my session, Auditing Data and Answering that Lifelong Question is at the end of the day yet. Now, if you're not familiar with that question, don't worry about it. We're going to go deep into that one in the next 45 minutes or so. So what are we going to talk about? Heads up, it's not going to be .NET related. Wait, clicker. Yes. So what are we going to talk about? We'll start off with looking at Nielsen's architecture, and we'll eventually see how it really had little fires going on everywhere, especially in regards to data arrival rates and data visibility. We'll start delving into that end of the day question, and we'll really understand that need for an auditing subsystem. We'll then start designing our auditing data, understand how it looks like, we'll store it, we'll query it, we'll maybe finally get an answer to that end of the day question, and then some alerts and add-ons to top it all up. But first, who am I? So, who am I? I'm Simona. I'm a senior big data engineer at ADOC, but I was working for Nielsen previously, so this is totally based on a true story. I love data. I've been dealing with data for the past decade now, which feels like a lot. I love music. The weirder, the better, and I love traveling. So basically, this is me in a slide. Now, I'd like to hear a little bit about you guys. How many of you are actually data engineers? You can raise your hands. Awesome. How many of you are software developers? Amazing. How many of you work on AWS platform? Cool. Yes, great. So let's start talking about Nielsen's data infrastructure. So what you see before you is how Nielsen collects data. More than 60 terabytes of data, billions of events flow through this architecture daily. And we'd collect them from various devices, so computers, TVs, cell phones, and they first and foremost would flow into the front-end layer, and more specifically, the data serving infrastructure. Now, the data serving infrastructure is written in Java. SLAs are very, very important to them, being that front-end layer for all of these events. They collect these events, they enrich them, and they produce them to their very own Kafka. So it would be very important to mention that at the time that this architecture slide was designed, we were running the front-end layer regionally. What does that mean? We'd had several data centers all across the world, and each and one of these data centers was running its own front-end layer. So the data serving infrastructure collects these events, enriches them, and then produces them to its own regional Kafka. From there, the data gets replicated using the uReplicator into the one single Kafka on AWS. So we're already in the data layer. Then we have the data loaders. These are big, robust Apache Spark streaming applications. They're responsible for consuming that data, deserializing it, and then eventually storing it in RDR. RDR, that just stands for Raw Data Repository, and that's our data lake sitting there on S3. We then have our data processors. These are big, robust Spark jobs. They consume that data, enrich it, aggregate it, and then eventually store it in all of these different data stores, and even back into RDR. And if we talk about the applications consuming this data, some of them consume it all together through Hive, and some through each and one of these dedicated data stores. And I want to take a little moment into explaining some of the things I talked about. So in regards to Kafka, we were using Avro format across all of our topics. Avro format, for those of you who do not know, is a serialization format, and you can actually use JSON just to define all of your data types. And we'll later on see how this actually made our job really, really easy. We use schema registry to store all of our schemas. And the chart that you see before you is a very classical chart. So you could see that in a lot of organizations. And if we take a moment to actually just look at the data lake, we'd have several buckets on S3 AWS. Each bucket was just dedicated to a different topic, and we were saving our data in daily folders. So you have a bucket for a topic, a daily folder, and just Parquet files. If you're not familiar with Parquet files because you're not a data engineer, then this is just an open source columnar format that just makes consuming and accessing that data later on easy. And this architecture really had little fires going on everywhere. And what we'll do now is we'll just start discussing all of these little fires, so you'll really understand that need for an auditing subsystem. Cool. So first thing, I really want to zoom into this connecting point. So what's happening here is that the data is being produced to the regional Kafka, and then it's being replicated using the uReplicator into that one single Kafka on AWS. What could go wrong? Well, several things. If you're not familiar with the uReplicator, it's a project made by Uber based on Kafka's own mirror maker in version 1. So aside from the most obvious problems, like the uReplicator crashing, data is not being replicated, some things could be even worse. So at Nielsen Israel, we had some pretty big topics. Some of them were more than 1,000 partitions big. And sometimes, just sometimes, the uReplicator would get stuck on some 5 or 10 partitions. So most of your data is being replicated, but just a little bit is not. Next, let's talk about this part. So this is what happens after the data arrives into Kafka on AWS. So as I've already said, we had the data loaders. They consume that data, deserialize it from Avro format, store it in Parquet on S3. What could go wrong? Well, several things. Kafka brokers crashing. Someone set the unclean leader election variable to true. Suddenly you get an entire partition wiped out. Spark streaming applications are crashing. Alerts start popping up. Bottom line, data is being late to arrive to RDR, or it's not arriving at all. And while talking about all of these pain points, what didn't I mention? Well, I actually didn't even mention how we recovered from all of these failures. And moreover, what was our criteria for recovery? Well, if we talk about this point again, uReplicator crashing, data is not being replicated, we'll just start the uReplicator back up again. We can see the data is being replicated, we can see that it's flowing again, and at this point we'd say, okay, great, problem solved. And very similar scenarios for this part. So data loaders crashing, Kafka brokers crashing, we just start them back up again. So cluster status is back to healthy. We can see the data is being consumed again. We can see that the data is flowing again. And at this point, we'd say, OK, great. Everything's fine. But we didn't really know any of the implications that these crashes and failures were having on our data. We didn't really know if we had any data duplication or data loss. And Nielsen is a data company, so data integrity is very, very important to us. And at this point, I really want to start discussing that end of the day question and why it is so important to Nielsen. And to get you to understand that, I really just need to take you to Nielsen's world, to the media world. So what we'd want to do at Nielsen is count unique users, and we want to do that on a daily basis. So how many unique users do we see per day? So essentially, you'd want to run your processor, your aggregator, only on a full day's worth of data. So that would mean only when yesterday is over, right? Because if you run your processor on partial amounts of data, you would have to run it again. And dealing with more than 60 terabytes of data per day, that would cost you quite a lot of money. So the question of the end of the day is just a question of, can I run my processor now? Has all of yesterday data actually arrived into the data lake? And at first, we tried solving this problem with a pretty straightforward solution. We said, okay, what time of day would yesterday be definitely over? Okay, so we said, okay, probably like 7 a.m. 7 a.m. yesterday is definitely over. And we set our processor to run at 7 a.m. But then this one time, we had this pretty big Kafka outage. No data was flowing whatsoever. We couldn't solve it by 7 a.m. Data processor started running, and we were back at square one. Then we said, okay, we store our data in daily folders, right? How about we use AWS S3LS, and we use that timestamp as an indicator, the timestamp of the last file that was written to the folder. But then this one time, the replicator wasn't working for one of our regions. So our processors took that as a signal that the day was actually over, and they started running again on partial amounts of data. And again, we were back to square one. And I think that if we look at Nielsen's data architecture again, you'll really see what I'm talking about. So there's a problem. There's a problem with Kafka. There's a problem with the data loaders. Bottom line, data is being late to arrive to the RDR. Data processors, not aware, they start processing all of these partial amounts of data. They store all of these partial aggregations in all of these different data stores. But the problem doesn't actually end there, because it's not only the data processors that will have to reprocess their data. All of these applications, reports, BI, billing, data science, they actually build their own data sets on top of all of these data stores. So they will have to rebuild their data sets as well. And so I think if you look at this architecture slide again, you'll really agree that it had little fires going on everywhere. And so for these two reasons, first one, just being able to understand the implications of all of these failures and crashes on our data, and B, being able to answer that end of the day question, we've decided to design our auditing subsystem. And what we'll do now is I'll walk you through the key points that we need to keep in mind to design our data. So the first point is just the fact that we had several topics. We didn't have one. And that number was not set either. So if tomorrow we have a new need, a new data type, we might define a new Kafka topic. The next several set of points has to do with the data serving infrastructure. And I've mentioned some of them before. So I told you that the data serving infrastructure is written in Java. It's not running one process, it's running two processes. And each and every one of those is actually running against a different set of topics, according to its own configuration. Another thing is the fact that they don't use a simple Kafka producer. They use a wrapped up version, a Nielsen Kafka producer. And of course, as I've already said, SLAs, very, very important to them. Last but not least, of course, as I've already mentioned, we use the Avro serialization format across all of our topics. And as I've already said, this is going to make our job really, really easy. So last but not least, why is the word window written on my screen? What does that mean? Well, the auditing window is going to be our metadata object. Can you guys see the Avro definition all okay? Cool. So what do you see? You can see everything that I've mentioned. We have topic, server, process. So for every topic, for every server, for every process, we're going to just count the number of messages being produced. But we can't really audit forever. We have to audit for a specific time frame. And that's exactly our auditing window. It's that defined time frame that we're going to audit for. So for every topic, for every server, for every process, for every auditing time, we're going to keep account of the number of messages being produced. Essentially, we're identifying every producer in this massive scale system, and we're enabling auditing for it. Now, if you're wondering what is the optimal auditing window and how big it should be, it really depends on your scale and throughput. We've set it to be 5 minutes. We wrote our code in such a way that it was completely configurable. We never changed it ever since. 5 minutes was just fine. And what you see before you is just the Avro definition that has everything that we've discussed. So now that we have this audit window objects, our metadata, we still need to connect it to our actual data. We're going to do that using a new object, a new Avro object that is going to be called the audit header. And the audit header is just going to contain all of that complementary information that our audit window does not. So what does our data does not contain? Well, we definitely know the topic, right? Because we're consuming from that topic. We don't have the server, the process, and we don't have the window timestamp. If you're wondering why process ID is not up here, it's just because it's incorporated in the server name. And if you've noticed the sequence ID and you're wondering why I didn't mention it, it's a bit of a spoiler, and we're really going to discuss it later on. So now that we have our audit header, we still need to make it part of our actual data. The first thing we're going to do is we're going to edit as a field in our topic. So if we look at a very generic definition for an Avro model, right? For example, for one of our topics, so we have, this is a very generic record, we call it raw event data, and we have a list of fields. And what we're doing is we're just actually adding audit header as the second field in this list of fields. Nice. But we still need to actually add that data in. It's part of our model. We still need to add it in. And we're going to do it using this piece of code here. It's Java code, not .NET. I'm sorry. But let me explain what's happening. So what we're doing is we're creating the audit header. It has the window time and the server name. Then what we're doing is, because we're processing all of these generic events, we're just taking this Avro record and we're checking its schema. So if that schema has the audit header in it, meaning auditing is enabled for this topic, we're just running it over using the object we've created. And it's really that simple, just because we're using Avro. So now we have the audit window metadata object that's keeping account for all of our producers. And we also have the audit header as part of our data. Where should all of this be? I really recommend that if you design an auditing subsystem for your Kafka, then you should really put it on your producer. So what we're doing is we're getting all of these generic messages right before they're being produced. If auditing is enabled for them, we're running over the audit header, we're incrementing the counter, and we're just producing these messages. And in context of everything we've just discussed, everything is happening right here. So everything's happening in the data serving infrastructure. And our data is just still being produced into that one regional Kafka. Cool. Now, the question is, of course, how we're producing that audit window metadata object. Because at first, being just like in Avro format, we've decided straightforwardly to just produce it to a Kafka topic. But then we noticed it's a bit silly, right? Because we're actually auditing Kafka using Kafka. So instead, we've just designed a really, really simple REST API. On AWS, you have the Amazon API gateway that allows you to do that. And so we just started shipping our audit window metadata objects through that API. And again, in the same context, so now on the AWS layer, we have that very simple API responsible for receiving all of these messages. Cool. So we have our data, we know what it looks like, we're producing it. How are we going to consume it? For the audit window metadata object, I've already explained, I've already mentioned that. So we're shipping it straight through the API. If we're still producing it to the Kafka topic, we of course can just consume it on the other side. For the audit header, it's just part of our data. It's going through exactly the same pipeline. So now our data loaders, they're consuming that data, they're still consuming it from Kafka, deserializing it, and just storing it in Parquet format with all of our data in the data lake. So we can just consume it from S3 using a very simple S3 consumer. Again, in context of everything we've discussed, so our data is still being produced to that regional Kafka, replicated to Kafka AWS, data loaders, spilling it into the data lake called the RDR, and then we have the S3 consumer putting it in the data auditing table that we're going to discuss in just a moment. And then the audit window metadata objects, they're shipped through the API and also arrive in the same table. Cool. Let's discuss that table right now. So we've decided to store all of our data in PostgreSQL. On AWS, you do have that service. It's called RDS. So we've chose RDS. We have a PostgreSQL there. Why Postgres? Well, essentially, the data is structured. Okay, it's definitely structured. We have a key that you should know all by heart right now. So it's the window timestamp, topic, server, and process ID. And we have our counter, right? Also, if you think about auditing data and the volume of auditing data, it's pretty similar to log data in terms that users don't actually want to look at data that's older than a month or two back. So just taking both of these factors into consideration, we've decided to store it in a PostgreSQL. In order to design our table, we need to understand what questions we actually want answered. The first one would be on what levels of granularity would we want our questions answered. So there are the obvious ones, like time granularity, for which we would use our audit window, and then topic, server, and process. But maybe something else? We're running several data centers all across the world. So why not get an answer on a regional granularity? Then we have arrival rates. That's pretty straightforward, right? So that's just how many of the messages that were produced actually arrived on the other side. But then we also probably want to know arrival latency. So that's just how many of the messages that were produced arrived within 2 hours or 4 hours. Cool. So let's understand how it looks like. You can see everything we've discussed. So we have the audit timestamp, the topic, the server, and the process. We have a location column, just because we're storing all of that data in the same table. So in order to differentiate between the headers and the metadata, we're going to use the location column, the event count, and we also have our add-ons. So we have region and we have insert time. And just deducting insert time from audit timestamp, we'll be able to calculate arrival latency. Nice. So I have an anonymized version of this table here for you today. Some cool things to notice. Insert time and window timestamp. They are both in UTC. We had developers working in Israel. We had developers working in the United States. So keeping all of our timestamps in UTC was very, very important to us. Region, we just extracted it from the server name. I don't really recommend that strategy, but it was the quickest way to go, and it worked. You can see that location. We have Kafka windows. So these are our metadata objects. We have RDR headers. That's our actual data. Another cool thing to notice, in my opinion, would be the event count. So you can see that some of the event counts are pretty big, right? They're over 90K, 30K. But then you can notice that we have an event count of 0. How is that possible? That's pretty weird. Well, if you look closely, you can notice that the event count of 0 goes only for the location of Kafka window. So what's actually happening is that the auditing subsystem is working all the time. So even if that server is not receiving any traffic whatsoever, we're still going to create all of these metadata objects and ship them to the other side. So they're going to arrive with an event count of 0. So that's just a really nice indication that the auditing subsystem is still working. And I think that's really cool to notice. Cool. So what you see before you now is the logo for Apache Superset. If you're not familiar with it, it's a BI tool under Apache. And that's a BI tool that we've used at Nielsen Israel for all of our data visualization needs and also for data auditing. So some nice charts. We have the data arrival rate within 3 hours. And you can notice that the number is a bit higher than 100. And yes, we did have data duplication. And you can say that, yeah, but with over 60 terabytes of data, having that 100.22 is nothing, who cares? But when you see that number go over 160 or 200, you know that you're having a problem. Some more nice charts. So it's just the data arrival rate for 1 hour and 24 hours. And I think that's really important to be able to just have these metrics and also being able to visualize them. And then also just the query that we've used to create these charts. So it looks complicated, but essentially it's very, very simple. And we're just calculating arrival latency here and deducting the insert time, the window timestamp from the insert time in order to get that arrival latency metric. What you see before you now is, again, the logo for Apache Superset. And we were seeing that quite a lot while our queries were loading for a really long time. And what I want to do now is just give a little shout out to my dad. My dad, who is a DBA and programmer for 20 years more than me. And when I came to my dad with a query that was running for 1 minute, he didn't give up. And he made it run for less than 10 seconds. So thanks, Dad, who's probably watching. So how did we do it? How did me and my dad optimize a data auditing table to be able to give us answers in a reasonable time? So the first couple of things we did were pretty basic. We've defined weekly partitioning, which is not as easy as it sounds with PostgreSQL. And of course, we created indexes, so unique indexes and complementary indexes according to the queries and their predicates. There's another set of variables that if you use PostgreSQL, especially on RDS in Amazon, I really recommend you take a look at them. So these are max worker processes, max parallel workers, and the max parallel workers per gather. And so these are the ones that really improve your performance, especially when you run your queries in a distributed way. And so you would be amazed at what this can do to your query when you use 10 workers instead of 2. Last but not least, I know that we all think that the optimizer knows best, but you'll be amazed at how you can trick the optimizer if you just use a union instead of an in predicate when you have several values that you want to compare to. I really encourage you to check that. So if you're wondering if you can actually create weekly partitioning in Postgres 11, I guess that's something pretty basic that we have in most databases today. The answer is definitely no. You can't do that with an automatic fashion, and you will have to create a scheduled process to do that. I used Apache Airflow. So Apache Airflow is the scheduler that we'd use at Nielsen Israel. And the way I did that was just by using very strict standards for my partition names. So just using pretty basic queries in your DAG, in your workflow that you schedule, you can create these partitions on a weekly basis. The last thing we did was just offloading data to history. Being a data company, being a data engineer, I don't really enjoy throwing data away. So I said, hey, instead of deleting all of that old data, I can just offload it. And then you can just actually create a job to your liking with the metrics that you like and aggregate on a different level of granularity. You don't have to actually keep it with the auditing timestamp. So just aggregating on an hourly granularity or on a daily granularity, and just keeping all of that historical data. Nice. So let's get to the point. Do you think that we can actually answer that end of the day question now? Spoiler alert, we can. And I have that pseudocode here for you. So the first thing that we're going to do is check the validity of the input parameters. But I'm just kidding, we're not going to do that. What we're going to do is just see what are the main questions that we need answered in order to see if the day is over. So the first one's going to be, what's the data arrival rate for the entire scope? So if we're checking for yesterday and the data arrival rate is below our threshold, then for sure the day is not over, and we don't need to check anything else. But let's say that the data arrival rate is just fine. The second thing we're going to check is the number of audit windows. Because if the number of audit windows is below what we'd expect, then there might be a problem with the data auditing subsystem, and we can't really trust it. But let's say that the data arrival rate is just fine, and also the number of auditing window is also okay. The last thing that we're going to check is the data arrival rate for the very last window. So in our case, the window for 5 minutes before midnight across all of our auditing windows. Why are we doing that? That's pretty weird. Well, if you remember when we looked at the superset charts, I told you that sometimes we'd get a data arrival rate that was higher than 150 or 200. Sometimes we'd get a data arrival rate that was really, really low. So at this point, we realized that we might get a calculation, a skew in our calculation of the arrival rate. So we said, okay, let's use the arrival rate for the very last window just as an indicator to whether the day was over or not. So only if the data arrival rate for the entire scope is just fine, and the number of audit windows for the entire scope is also okay. But also, the arrival rate for the very last window is also great. Only then, yes, the day is actually over. So now that we can answer that question and we know that it is the end of the day, what we wanted to do was give our developers, our big data developers, the ability to schedule the data processors, schedule the jobs according to the answer of the end of the day. That we've created a very simple end of the day API. What you give that API is a simple question. So for a topic, for a scope, right, for a date, and for a specific threshold, is my day over or not? And the answer would look something like this. So for example, this is not the end of the day. Sad smiley face. Why? Because basically the current arrival rate is below our threshold. But here, the reason is different. So we can see that the reason is just that the last window did not arrive entirely yet. And then here, yes, our day is definitely over. The threshold is fine. The number of windows is fine. And also, that very last window arrived entirely. Cool. So at this point, I just want to start discussing alerts and add-ons. Because having all of our data, we can schedule our processors, we can see if it's the end of the day, but we're not done yet. Because we were having all of these failures, we were having trouble investigating this huge architecture. So what we did, we've defined a couple of SQL queries as the one that I've showed you before in order to actually define alerts. So how would these alerts look like? Exactly like this. And this is a real star for me, because these alerts were popping up faster than any of the heartbeat alerts of Spark or Kafka, than any of the failure alerts of our jobs. These were getting there first. And that problem with our view replicator, when it's being stuck on some 10 or 50 partitions, no one could discover that. No alerts, only the data auditing alerts. And moreover, when you see that you have an alert on a specific region, you can know for sure that the problem was with the view replicator, not with your Kafka, not with the data loader. If you see that you're getting an alert on a specific topic, then you know that the problem is probably with the data loader and not with your view replicator. So this really made our life a lot better. And now we can discuss detecting duplications. So if you remember, when we looked at the auditing header, I told you, hey, here's a sequence ID, but that's a bit of a spoiler. Well, we're going to discuss it now. When we started seeing these arrival rates that were higher than 100, we said, okay, we probably don't have data duplication. The problem is probably with the data auditing subsystem. So we thought about a way of how to check that. And what we did, we simply added a sequence ID. So that would be a running sequence ID for every audit header. So your audit header is unique, right, for every window, for every producer. And when you added the sequence ID, it really makes that audit header for a specific message unique. So in order to detect duplications, because all of our data arrives to S3, all you need to do is just read your data using Spark into a data frame, right? It's an audit header, it's in Parquet format. And then if you aggregate on the audit header and count the distinct number of sequence IDs, you get the amount of duplications. We were having duplications. It was not a problem with the data auditing subsystem. And with this, I'm done. So if anyone has any questions, I'd be really happy to answer. Okay, then not. So thank you for coming, and enjoy the rest of your day.